Okay, I just want to use technology to do some things with the polar form and get the polar form and so forth. Um, so as far as declaring symbolic variables, it might not hurt to have something like this at the top of all your files. Now, whether I end up using them or not, I don't know. So what I might do is comment them out, but this is the idea. I made z symbolic, but I made sure it's a complex variable by saying domain equals complex, and then I'm making sure that x and y are real variables by saying domain real. But I may not even want z as a symbolic variable to begin with, or something like that. But because like right now I'm just gonna choose it as something. So suppose I let well, actually I'm gonna do z1, I guess. So suppose z1 is 3 plus 2i. So I have that. Then actually I can get both the modulus, or the absolute value, and the argument from this simply using those commands. And so if you want to go to the polar form, we can do something like let's see, so what do I want? Oh wait, let me use so that I actually know what the answer is. Let me use 4, because this makes a 3, 4, 5 triangle, so I know the modulus of this is 5. I'm not sure what the argument is, but I know what the modulus is. And so let's just show z1 dot, or no, I think I just want ABS of z1 like that. Then I'll do my comma. Oops, that's not a comma. Do my comma, and then do arg. Arg's not showing up in nice colors. Let's see what happens, and we'll try it a couple different ways. But again, part of the reason I do this is to show you it's okay to fail, on this. So it says the arctangent of 4/3. Well, that's true. Interesting. So, arctangent of 4/3. Okay, kind of like a number there. So let's try doing this, doing a dot and then an n. Now the dot n is to get a numerical equivalent of that. So let's do that, and there we go. 0.927 radians. Okay, so that's in radians. You could look up if there's a nice conversion from radians to degrees if you wanted it in degrees, but this will be fine for what we're trying to do here. So now let's take another one. Z2 is equal to, let's see, I need another Pythagorean triple that I know. What do I know? Let's see, 36, that's a 6. Do we know how to make 36? No, that's 27, that's a cube root. What's the, let's see, was it 5 and 11? See, I'm thinking out loud. You can tell I wasn't prepared for my Pythagorean triples on this. Shout one out to the video if you know one right off the top of your head. But I think 5, 12, and 13, I think. So 5 plus 12 times I for Z2, and then I'll just do the same thing. Control C for copy, Control V for paste, change those to 2's, and hopefully I'll get a 13 here. Yes, 13. Okay, now, so when I multiply these two numbers, Z1 times Z2, I should get a modulus of 5 times 13, which is what, 65, and an argument of 0.9 plus 1.1 here. It looks like it'll be about 2.1-ish is what I should get for that. Okay, so let's let Z3 equal Z1 times Z2. Now let's take a look at that number. So let's show Z3, but then let's also show then its modulus or absolute value and its argument, and evaluate. And so we get 56I minus 33, and there's our 65 and our 2.1 to see that indeed when we multiply two complex numbers, we see that their modulus, their moduli, or actually the two of them are multiplied together to get the 65, and the arguments are added to get the 2.1, and so there we go. There's a little bit with the polar form and how we can get it. Now if you have the polar form, right, if you have the polar form, well, you've got the angles, so you can just use cosine and sine, you know, r, if you have r, so you just use r sine theta and r cosine theta for, well, actually r cosine theta for x, r sine theta for y. You know, so if I had the arguments, I would just use the cosine functions, and then if I had the modulus, you know, I would do it that way. But there you go. I think that kind of does it for just a quick use of the polar form within SageCell. So get out of here.